Hey everyone, and welcome back to another video from the Wise Tutor. This video is going to be introducing you to differential calculus, and more specifically looking at the concept of a rate of change and extrapolating that into an instantaneous rate of change, which we refer to as a derivative. So this is the first video of the introduction to differential calculus, and we'll be going over applications, anti-differentiation, and so on and so forth. And this plays a real basis for a lot of the stuff that you work on in Year 12 methods, and if you study maths in university as well. Calculus, I think, is really central to a lot of areas of STEM study especially. So if we move into the unit outline, what we're going to have a look at is the gradient of a tangent, and looking at how the gradient of a secant, from one point along a function to another point along a function, and see that that represents the average rate of change of the function over that period of time. We're going to be looking at how we can get that secant to approach zero, what that kind of looks like and what it means. It means an instantaneous rate of change of a function. And then we're going to be having a look at formally introduce this concept of a derivative. So what is a derivative? How do we derive a derivative? And some of the notation that we use when we represent derivatives. So let's get straight into the video. So if we have a set of axes here, we have our x-axis here, we have our y-axis here, okay, and we consider a function along this axis, and it can be any function, and that's the whole point. It's a generalized function. So this is our function here. We call this function, let's call it fx. It does happen to look like an exponential function here, but for the purposes of this, let's say it can be any function. And then let's say we pick a point along the curve and another point along the curve, and we draw a line connecting those 2 points up. So there's 2 points there. Okay. So if we consider this will have an associated x value, and let's call it x. And this will have an associated y value, and let's call that value y. And then this next value will have a separate value x, but for the purposes of this, let's consider this as an x plus h. Okay, so we've moved h units in the x direction. And y in this case can be represented as a function of x, so we could equally write this here as f of x, and this point here would be considered the point f x plus h. And so if we wanted to consider the rate of change of the function, let's say the easiest way to conceptualize this is if y represents displacement and x represents time, for example, then we know that that speed is generally equal to displacement over time, or just displacement over time in this case. So we know that the gradient of this function, as in this difference in y over this difference in x, the rise over the run, is going to be equal to our speed. So that's our rate of change of distance over time. When we're talking about a function in terms of y and x, we're talking about the rate of change of y with respect to x. Okay? And so the average rate of change of y with respect to x over the point x to the point x plus h, okay, the average rate of change here will be equal to the rise, which is f of x plus h minus f of x, divided by the run, which is x plus h minus x. And so that simplified will translate to f of x plus h plus f of x over h. Okay? And so what this represents is the difference quotient. Okay, and what it represents is the average rate of change of the function f. And more specifically in this case, it is a representation of the rate of change of y with respect to x. We can also equally represent this change in x over here, this period here, as the change in x, or delta x, and we can also represent the change in y here as delta y. And in doing so, what we are doing is we are adopting a form of notation called Leibniz notation, who was one of the people who independently discovered calculus alongside Newton. And so where Newton's formula involved f of x plus h plus, sorry, this should be a minus, f of x plus h minus f of x over h, where Newton's formula involved this, Leibniz's formula was more accurately represented as delta y, the change in y or the rise, divided by delta x or the run. 424. And so delta y over delta x is equal to f of x plus h, take f of x over h. And so that also is equal to the average rate of change of the function from x to the point x plus h. And delta x here would be equal to h. Okay, and so we've knocked off this point here, we've knocked off this point here, we've knocked off this point here, and we also have knocked off this point here. So now let's introduce the concept of a derivative. So if we consider our set of axes again, and we consider our function f of x, we can derive the concept of a derivative. And this is the first principles approach to deriving a derivative. It's a bit of an awkward terminology I'm using there, but getting our derivative. So we have our y as a function of x. This is this curve is f of x, y equals f of x, and we've got our point here that translates to x and f of x, and then we have our separate function. Okay. Alright, and we have our separate function here, x plus h, which maps onto f of x plus h. And so, maybe we should draw this line a bit better. Okay, so let's say this is our function here, and we have our f of x plus h, take f of x, over x plus h, take x, which is equal to f of x plus h, take f of x, over h. And so this is the average rate of change of the function, and as we decrease h, we get a secant that steadily comes closer and closer to our point x, okay? So we have our secant steadily coming closer and closer until eventually, when our h is equal to 0, we essentially have a point rather than a secant. And at that point, the gradient of the secant is approaching the gradient of a tangent drawn to that line. And so here, the tangent drawn to the line is referred to as the instantaneous rate of change of the function f of x at the point x. And the way that we represent this using limit notation is we represent the instantaneous rate of change at x as the limit as h tends towards 0 of f of x plus h, take f of x, over h. And this is referred to as the derivative of the function f of x, and we can represent this in Leibniz notation as dy dx, or we can represent it in Newton's notation as f dash x. Okay? And so that is the derivative at a certain point along a function. If we used Leibniz's notation, this would be represented as the limit, as, remember, this is delta x, and this is delta y. The limit as delta x tends towards 0 of delta y divided by delta x. Okay? And so this is what our Leibniz's notation would refer to as the derivative of the function f of x, and that is equal to dy dx. It should be noted as well that dy dx and f dash of x both mean the exact same thing here. And so here we know that the derivative, or the gradient of the function at the point x, or the gradient the secant starts tending towards as our secant approaches the point x, is going to be equal to the gradient of the tangent line of the graph y equals f of x, also known as the instantaneous rate of change of the function at the point x. And so that is the concept of a derivative. And this is something we're going to hash out a little bit more in some of the following videos, where we talk about the power rule and different applications as well. But this is referred to as first principles, and it is how we derive this branch of mathematics known as calculus. So, in this video, we introduced the difference quotient in terms of both Newton's form and Leibniz's form, and we introduced the notation Leibniz and Newton for representing derivatives as dy dx or f dash of x. So this is Newton, whereas this is Leibniz. We also had a look at a difference quotient as h tended towards 0 or delta x tended towards 0. We had a look at, as I said, we mentioned the Leibniz and Newton notation, derivatives. We interpreted the derivative as the instantaneous rate of change of the function f of x at the point x, and also determined the slope of the gradient of the tangent line of the graph. And so this should read the 16th of November. And so the next video, where I'm going to be going a little bit more over concepts in differential calculus, will be released on the 16th of November, so on Saturday. Remember to comment if you have any questions regarding any of the content in this video, and I can add that in supplementary content at the end of this video series. And make sure that you subscribe so you don't miss any new videos. Thank you guys. I'll see you on the 16th of November. Bye.